Okay.
Okay, so it's a pleasure to introduce this week's lecturer, Ryan Williams, who is here now and of course when he's not here at MIT. And we are promised, or at least have the implicit promise of having satisfaction guaranteed by the lecture. Looking forward to it.
Yeah, I think the first thing I want to say is that I'm not guaranteeing 100% satisfaction. But the story today is mostly mathematical, but it's also personal. And I think there are quite a few meta level points too, which are broader than the content. So I hope they'll resonate in some way. So our starting point is the P equals NP question. In this talk, I will only think of P and NP quite informally. This level of formality is more than enough to understand what I want to convey here. So informally, NP is a set of problems where verifying a solution of the problem is easy to do. And P is a set of problems where finding a solution is easy to do. And our notion of easy is that of polynomial time. There is some algorithm. I don't necessarily care about the algorithmic model. There is some algorithm solving the problem, so giving me the correct answer on all inputs, and P of n steps for some polynomial P on all inputs of length n. Okay. So a canonical example of an NP problem, and the focus of this talk is the Boolean satisfiability problem, or K SETH for a parameter K that I will describe. So our input is a Boolean formula. It's a conjunction of a bunch of little clauses. I mean, I could use like the laser point here. Laser pointing with the actual laser pointer might be difficult. So we have a formula, which is a conjunction of these little formulas, which are clauses. Each clause is an OR of variables or negations. And I restrict each clause to have at most K of these variables. So K is the so-called clause width. Yeah. So this is a so-called conjunctive normal form. And the output, the desired output, is a true-false assignment to these variables that makes the formula true, or some special no answer if there's no such satisfying assignment. This is the way when I think about the SETH problem. Okay, so just to give a very simple example here, we're forced to set x to false, and then we just split y and z to be true and false so that the other two clauses are satisfied. Okay, so if I give you a true-false assignment that makes the formula true, it's very easy to verify. You just plug it in and check. But the problem of constructing such a true-false assignment from scratch seems very hard to do.
Why is not M a parameter in addition to K?
Sorry, this M, the number of clauses?
Yes.
Oh, so without loss of generality, for a fixed constant K, M is big O of n to the K. Right, there's only so many possible clauses. Yeah.
Oh, yes.
So it's a polynomial. Yes. Yeah. So we don't necessarily care about n. We can track it with the number of variables. Okay, so here's the problem again. So I have a very simple logical formula, and I want to know, is there a way to set its variables to make it true? Okay. So of course the problem is solvable. It's a finite problem with a finite search space. Trying all possible assignments will solve it in about 2 to the n time. Of course, you have to plug it in and evaluate it. But the question is sort of how quickly can we compute satisfaction or determine it's not possible? Is there a faster way? This is one of the many ways that one can think about P versus NP. So we have a dumb algorithm for solving a problem, and we just want to know if it's possible to be any smarter. Okay. And the Cook-Levin Theorem from the 70s shows us that K-SETH is actually a very fundamental problem from the point of view of P versus NP. So for all K at least 3, for example, 3 SETH, this is NP complete. turns out the problem is easy for k equals 2. But for k at least 3, it's NP complete, meaning that if we can show that k sat is not in polynomial time, it's not easy if and only if p is different from NP. So the entire difficulty of the P versus NP question is already wrapped up in like how complicated is this k-sat question? How complicated is 3-sat? Can we solve it in real time or not?
Is it easy to see that if you have it for k equals 3, you have it for k equals 4 also?
Yes, there's a way to encode 4-sat in terms of 3-sat by introducing new variables. Yes. Absolutely. Yeah. So, the Cook-Levin theorem, the way that people have thought about it traditionally, like it was that it says that every NP problem, so each of these problems where you're trying to find a solution or verify a solution, you can efficiently encode it in this programming language k-sat. So, like let's say the problem of 3-coloring a graph. Let's pick another NP complete problem. It can be encoded in Boolean logic. All right. So this is some, viewpoint of this is some reason that the SAT can express all of these other problems inside of it. But the Cook-Levin theorem has turned out to be an extremely useful tool in practice. So already in the early 2000s with the solver grasped by DeMarcus Silva and Sakala, and the solver Shaft, which was developed here at Princeton by Sharad Malik and his group. So they began to actually solve CNF sets, so this conjunctive normal form set faster. And there's a whole article in the Communications of the ACM on this revolution. So now they're incredibly well-engineered CNF sat solvers that can be used in principle for solving any NP problem. And for many practical problems, the fastest known way to solve them is to convert them into one of these CNFs, this ands of like little clauses, and then just run a solver on it. So it's a triumph of the Cook-Levin theorem in a certain sense, because you can optimize a solver to not sort of worry about any domain-specific knowledge for your problem and just let your reduction from the problem to SAT handle that.
Could you give us a sense of like the what value of n could I practically solve in a day today?
It really depends on the type of instance. So, but there are instances on millions of variables that get solved routinely every day. Now, do these millions of variable instances encode like any arbitrary problem?
I see.
No, but I'll get to that in a minute. But yeah, no, they can solve extremely large instances. So is SAT a solved problem? Given this, and no, okay, big no. So it's very easy to cook up examples which make practical SAT solvers essentially run for forever. So examples which encode integer factorization, for example. So I give you a multiplication circuit and an output, and I want you to find like an input that makes the multiplication circuit output a product. These are extremely difficult for SAT solvers, and they're actually common. Like, so if you have a sufficiently difficult math problem and you encode it in SAT, you manage to do that and run a solver for a large enough n, it's probably not going to work. But it just turns out that a lot of instances people want to solve in practice have structure that these SAT solvers can take advantage of and solve. Okay.
But they're robust in the sense that they work polynomial time for most of examples.
Well, so most is a big loaded word here, right? So
in that sense, they're robust.
Sorry, what do you mean by robust?
On the previous slide, there was this.
Yeah.
So you're saying that you can apply these solvers for some cases, like.
Yeah. So what happens in practice is that, let's say, okay, let me try to give you some informal idea of why instances in practice. Like huge instances in practice are not like arbitrary random instances or whatever, right?
Okay.
So let's say I want to verify like some hardware design. Okay, somebody over here built the multiplication circuit, some team over here built it. Some other team built like, maybe like some other basic function. And then there's maybe some pipelining going on in my processor too. And this processor is not designed by one person, or, it's designed by a huge group of people, and they're split into sort of teams, and there's an interface between them, right? So these things are extremely modular. And so when you reduce this thing to a set instance, there's going to be like a small set of variables that are kind of bottlenecks between like the modules. That if you manage to set those correctly, if you're trying to, so let's say I'm trying to solve SAT to like find some input in which this circuit fails to do what I want it to do, right? So there are some variables that just like have a lot more weight on. They're just that much more important than others because of the way things are designed in the real world. That's all.
So how empirically.
Yeah, but we don't actually have like a formal scientific explanation of why. And the SAT solver community is constantly at war over this, actually, about why SAT solvers actually work in practice. Because, yeah.
So will you explain for which problem it works and for which it does not?
Yeah, that's not the focus of this, but I'm not going to, but we can talk about it later yet. Yeah. So indeed, we still believe P is in from NP, despite the SAT revolution in practice. And in fact, people believe stronger hypotheses, P from NP. So exactly how hard is the SAT problem? Well, saying P from NP just means that, say, 3 SAT is not solvable into the C time for all constant C. I give you a formula of, let's say, on n variables, it cannot be solved into the C time for every constant C. So into the billion, whatever. But does the 3 SAT problem require 2 to the n time, right? We know there's an exhaustive search algorithm. Well, to start off, no, okay. Again, there's a very, very easy way to see that it doesn't require 2 to the n steps. So given any clause on 3 variables, say x or y or z, there's only 7 out of the 8 possible satisfying assignments, right? If I set them all to false, that's no good, okay? So I could just like try the 7 possible choices for which are satisfying, okay? Plug them in, okay? Now I have a formula of 3 fewer variables, and I can recurse, okay? And so I avoided a large swath of the search space by doing this, by avoiding like the assignment where all 3 of these were false, okay? So this will give me about 1.9 then at time already, okay? So it's a very, very simple algorithm, okay? So this is not a problem that requires exponential time, but nevertheless, we can ask questions which become very interesting already. So similarly, you can solve k-sat in 2 to the k minus 1 to the n over k at time. The idea is that there's only, so given a clause of length k, there's only 2 to the k minus 1 possible satisfying assignments out of the 2 to the k. And if you plug one of them in, you reduce the number of variables by k. So you'll do that at most n over k times, right? And these will always give you exponents which are strictly less than 2, or these base of exponents strictly less than 2. And so the conclusion we can get is that for all k, there is some delta less than 1, so that k sat is in 2 to the delta n time. So we can always solve a little bit faster than 2 to the n time. Okay. However, as this clause width k, like this bound on the number of variables I can have inside of a clause, as it grows unboundedly, this delta goes to 1. Yeah. And so I'm back to 2 to the n, essentially, as k grows unboundedly. Okay. But all known k-sat algorithms have this deficiency. So there's algorithms based on local search, sort of starting from a random assignment, trying to fix it. Algorithms based on backtracking, sort of trying to plug in an assignment starting from nothing. Algorithms based on dynamic programming. Like all of these have this same sort of deficiency. So this leads to some conjectures about like how difficult this k-sat problem is. So here's 2 major conjectures about SAT that go far beyond asserting that P is in from NP. So one is 3 SAT solvable in 2 to the epsilon in time for every tiny epsilon greater than 0. The exponential time hypothesis conjectures that the answer to this is no. Okay, so there's some there's some base of the exponent greater than 1 for which you're going to need that to the n time. So ETH is that 3 sat is 1 plus epsilon to the n time for some epsilon. Okay, or maybe another way to view it, it's just not in 1.001 to the n time for some number of zeros. Okay. So there's some base in which it's going to require exponential time, not to the n, but there's some exponential. Another question is, can we solve this k-sat problem in to the delta n time for some universal delta less than 1? It does not depend on k. And so it doesn't have this property that as k grows unboundedly, delta converges to 1. This is some universal delta. In the strong exponential time hypothesis, or SETH, conjectures the answer is no. Okay, so in other words, for all delta less than 1, there's some clause with k so that this k-sat is not in 2 minus delta n time. Okay. Another way of thinking about this is that if I don't put any bound on the clause, let's just look at this conjunctive normal form set, this ands or set, it can't be in 1.999 to the n time for any number of nines. So you can't even shave any tiny bit off the base exponent. So a theorem which is totally not obvious is that SETH implies SETH. You need some extra machinery to prove that kind of thing. But the thing I want to emphasize is that these much stronger hypotheses, far beyond asserting P different from NP, are totally consistent with our knowledge of the k-sat problem. You know, all these known algorithms that we have, including the ones that model solvers in practice. So we know how to cook up instances that will make solvers in practice run in exponential time, for example. And they will behave like this as this clause with k goes from 4 to 5 to 100. They will need more and more time closer to the end. Okay, so what can you do with these strengthened hypotheses?
Guys?
Yes.
Are these just options specialized for k-sat, or it's assumed that it's true for any NP complete?
Yeah. So I'm about to address this on this slide. So for this ETH thing, it turns out to be robust for a large class of problems. Like, because, I mean, if you think of the circuit set problem, right, with n variables, that's a different problem from 3-sat. And that one, that we'll say it's got n inputs. We don't know if it takes 2 to the n time or not. That's a big of a problem. So it sort of subdivides NP complete problems into different classes. And so already for like this exponential time hypothesis, just saying which problems need 2 to the epsilon n time, we can show that, so one can show this is like the consequence of a lot of different works. A lot of these other NP complete problems like independent set, clique and vertex cover, dominating set, whatever these things are, a bunch of canonical NP complete problems, they also don't have 2 to the epsilon n time algorithms for various epsilon greater than 0. Okay, assuming that 3-sat needs, let's say, 1.1 to the n time or something like that. Okay, so the ETH has many consequences similar to the hypothesis that P is in NP, although these reductions are often much more complicated. But what about this SETH thing?
By using the reduction of one problem to the other.
Yeah. So some problems you can do this, but you have to be very careful about like the n, the parameter n, because so in general, when I define a polynomial time reduction, I might take an instance of length n and blow it up to an instance of length n squared. Then having a sub-exponential time algorithm for that is sub-exponential n squared. Those kind of problems. You have to be very careful about the reductions. So there's like intermediate limits you have to apply to sort of make the instance like shrink to about like the size of the witness. This is called sparsification limits that people use to do this.
But it's not known to be false for any NP complete problem.
What do you mean?
There is a better algorithm for.
I'm not sure what you mean. Let's say the planar circuit set problem. I have a circuit in a planar graph. I want to solve it faster. You can solve this much less than 2 to the epsilon n time for reasons that I'm not going to describe right now. You can think about it. But yeah. So the exponential time complexity of NP complete problems is very different from like what you think about when you think about like the NP complete class. Yeah. Yeah. Right. So let me get to and so this is where my personal opinion comes in, and I think this is like an important point. So I believe that this SETH thing is false. I believe there's a faster SETH algorithm. Now, this ETH thing, I'm uncertain about. I don't know. I want to stress that my belief that the negation of this is true is definitely the minority opinion. Okay, I don't know if you knew that, but the chances I'll be proved wrong in my lifetime are basically nil. Like, not only do they have to separate P from P, they've got to like show that like SET requires basically 2 to the n times. So I feel safe that like I'm not going to be proved wrong. But actually, I don't care about whether I'm proved wrong or not from the point of view of this belief. So my pursuit of trying to find a faster algorithm over 20 years has failed so far. But even if it turned out to be true, my belief in its negation led me to a lot of ideas and results that I wouldn't have found otherwise. So this is belief in a fact, not necessarily because you have faith in a truth value, okay? But belief is a way to prime your brain to do research. So I found that if I pretend that SETH is false, and if I pretend there's some faster algorithm, I have to visualize what that algorithm could look like. Well, and what its consequences can be, like I'm forced to think about like how our algorithm could possibly solve this problem without looking anything like what we know. And so because I'm forced in this way because it generates ideas, why not believe it's false? Just operationally, why not just keep believing?
Do you have theorems which are proved by the dichotomy, assuming SETH and assuming negation?
Yes, I do. I have win-win theorems.
With Riemann hypothesis, very similar story, but there are proofs.
There are proofs of both of them. Yeah, well,
from both sides.
Many of these I proved just in recent years, so I'll need a few years before someone proves both of them. Yeah, right. So why not believe it's false? So yeah, this is actually a talk about a few significant failures and how they end up leading to something very interesting anyway. So I'll start with talking about something that led to an area now known as fine-grained complexity. And then I'll talk about how I accidentally became a circuit complexity theorist. And based on how much time I have left, I will talk about a new approach, which has a sort of win-win possibility. Okay. Right. So the problem with asserting something as strong as SETH, like CNF SETH basically needs to the n time, is that algorithms can do very unexpected things. Right? They can be magical. And so in grad school, I became enamored of some magical little algorithm of Vitae and Rode for finding triangles in graphs. So this is a very simple problem. You have an n-node graph. You want to find 3 nodes that are all interconnected. So there's an obvious n-cubed time algorithm, trying all the triples. And it turns out you can use matrix multiplication to solve it faster. So let omega, which is known to be at most 2.4, be the smallest, or could be an infimum, so that the smallest real, so that n by n matrix multi can be done in the omega additions and multiplications. So I believe in a sort of conservation of magic principle. If you find something that's sufficiently magical in one domain, it will yield magical solutions in other domains, okay? Works in mathematics and in real life, okay? So here I'm just going to show how magical matrix multi can be used to get magical triangle finding. So here's the theorem. In node graphs, triangles can be found in about into the omega time. So I have a search space of size n cubed, and I can somehow navigate it and search it in 2.4 time. Okay. So with no assumptions on what the graph looks like. Okay. So is this very, very simple proof? Okay, let A be the adjacency matrix of the graph, and let B be the product of the adjacency matrix with itself. Okay. And the observation is that this graph G has a triangle if and only if there's some ij so that aij is 1, there's an edge between I and j, and the product is non-zero in ij. Okay. And so this is what the product looks like. That, like, if the product's non-zero, that means there's a 2-path, okay, in the graph. And if aij is 1, that means there's an edge. That's it, that's the proof. Okay. All right, so just using matrix multiplication, okay, I can detect whether there's a triangle. In fact, for every edge, I can tell you whether it participates in the triangle or not. Okay.
Well, what feature of this algorithm makes you think of it as magical?
Oh, this is just a simple reduction. I didn't show you the magical part. Have you seen Strassen's algorithm? I mean, actually, should I show you Strassen's algorithm? No, I should not. Okay.
I mean, it's a beautiful algorithm, but you promised us all sorts of great things and maybe ideas of the future if we don't tackle it with too many questions. So we want you to proceed.
Oh, but I mean, Strassen might be nice because it shows something.
Yeah, that's the magical part. This is just a magic preserving reduction.
Okay.
This is not the source of the magic. Okay, yeah. So I have a slide. Right. So for example, n by n matrix multi can be done in about 2.8 additions and multiplications. Right. So here's the proof idea. So you start with an algorithm for 2x2 matrices that only uses 7 multiplications. So the story is that Strassen was trying to just show that 2x2 matrix multi needs 8 multiplications, and he failed to do so. So you construct these particular matrices from multiplying. So you have an A matrix and a B matrix. Okay, so you compute these 7 multiplications, and because I can't contain the whole algorithm on this slide, let me just tell you, one can recover all entries of the product by linear combinations of these 7 multiplications. Okay, some additions and subtractions. Okay. So the key insight is that this algorithm works even if the elements in the matrices are also matrices themselves. So you can apply it recursively. So it's a non-commutative algorithm. Okay. So then you can get an algorithm for 2 to the k by 2 to the k matrices using only 7 to the k operations instead of 8 to the k by running the 2 by 2 algorithm, pretending each element is a 2 to the k minus 1 by 2 to the k minus 1 matrix. And then when you need to multiply 2 matrices, as desired, you call the matrix multiplication algorithm recursively. Okay, and then you get this time recurrence, and it solves to what you. Okay. And the current best bound is much less than that, and it's a big open problem whether this matrix multiplication exponent should be 2 or is greater than 2, and there is not a consensus on that. Okay, so this is for example is a very unexpected magical algorithm, and you can use it to navigate the search space faster. Okay. Right, so could there be such an algorithm for SETH? So I have a 2 to the n time algorithm. I want something that runs in 1.9 n time. So could one embed a SETH instance into a large graph so that somehow finding a triangle corresponds to finding a satisfying assignment in the right way? Okay. So what would this mean? Right, I want to take a CNF SETH instance and want it on k variables, and I want to get a triangle finding instance on about 2 to the k over 3 nodes. Right, if I had 2 to the k over 3 nodes, right, then the naive triangle finding algorithm would take in like 2 to the k, right? So I have a search space of size 2 to the k. If my number of nodes is n, right, my naive triangle finding thing is n cubed. So if I could just apply matrix multi, if I could reduce CNF SETH to triangle finding, then I could get something that runs faster than 2 to the k times. But I failed because edges can only encode so much. Okay, let me just leave it at that. However, edges can encode constraints on 2 variables, And this led to a paper that showed that a wide variety of problems for which we didn't know better than 2D time algorithms actually have them. So for example, the max cut problem, where I have an end-node graph, I want to find a bipartition that maximizes the number of edges crossing from one part to the other. This can be solved faster than 2D time. Okay. And I also found other simple polynomial time problems, so that if I could solve them faster than some obvious algorithm, then I could also solve CNF set faster. Okay. And some of these problems turned out to be very fundamental. People have been working on them for a long time, and so they turn out to be part of this area now called fine-grained complexity. Okay. So one of the problems is orthogonal vectors. So I give you a set of n binary d-dimensional vectors, and my inner product is over the integers. So I want to know if there's 2 with inner product equal to 0. So for example, if I give you these vectors here, here we have an orthogonal pair. So there's no component where they both have a 1. So they're disjoint. You can think of them as disjoint vectors. All right. This is a very, very, very simple problem, right? And there's a trivial algorithm in squared times d time. Okay. But it's surprisingly tricky to reason about. Like if the dimension becomes some function of n, this problem becomes difficult to find a faster than quadratic time algorithm. Although, you know, it does seem like a very simple and very basic problem.
When you say orthogonal, it's orthogonal mod 2 or disjoint?
Sorry?
When you say orthogonal, is sum of product mod 2 0?
Oh yeah, it's a sum over the integers. It's inner product over the integers. Yeah, actually mod 2 it can be solved in nearly linear time. So yeah, mod 2 you can actually solve this quickly. Yeah. I can show you later. Yeah, you can get it n times d time. But over the integers, if you want to know disjoint vectors, then it becomes a hard problem. And in fact, it's as hard as solving SETH faster. So this is a polynomial time problem, okay, that if I solve a little bit faster than the quadratic time algorithm, I actually get a faster algorithm for CNF set. This is it's a bit strange, right? So I need the dimension to be about log squared n, or just something slightly bigger than log n. But if I can solve it faster than in squared time, I can get a faster set algorithm. So this is, you know, more along the lines of you know what I wanted. So I was hoping, okay, maybe there's a magical algorithm for orthogonal vectors. You know, there's one for triangle finding. Maybe I get one for orthogonal vectors. Yeah, if I have time at the end, I could show you this reduction. It's pretty simple in hindsight. So this orthogonal vectors problem is one problem. Another problem which comes up in computer science quite a lot is partial match queries. So I give you a database of n strings, which are d bits long, and I give you n queries that have wildcards. So the wildcards mean I'm okay with it matching to a 0 or a 1. Is there a query that matches a string? So I have these queries with wildcards, and this query here means that, like, just find me something that has 0, 0, and you can put whatever you want in this bit. You can put whatever you want in this bit. Okay. So I'll have like some queries and some database within strings. And for example, like these have a match. Like in the places where they're all the bits of the query match all the bits of the corresponding string. Okay. This is a very important problem in computer science. Like if there's no wildcards, you could simply set up a binary search tree on the database and search and find just look up the queries very, very fast. But once there are wildcards, it becomes, again, a quadratic time type problem. I need to apparently try all the pairs from the queries in the database and just check.
When you ask, is there a query that match, do you mean finding, does it exist or do you want to exhibit it?
Does it exist or do I want to exhibit it? Actually, these problems are equivalent. And in fact, it's like the problem of even finding one query that matches one string in the database, it turns out to be subquadratic equivalent to the problem of processing all the queries. So there's ways to show that these are actually all equivalent problems from the point of view of getting a subquadratic time algorithm.
What about a quantum computer? It would do this very efficiently, or?
Yes. With quantum, I mean, all these sort of search problems, you could save a square root essentially over like, yeah, because it's effectively computing an OR over a bunch of objects, right? So using Grover search in the appropriate way, you could do a square root of it. Yeah. But we don't know how to build this. But yeah, it's true. So it's not too hard to show that actually this partial match problem can encode the original orthogonal vectors problem. And so solving it in subquadratic time would also solve the CNF SAT problem faster. So there's a pretty simple reduction to show if you that you can encode orthogonal vectors as.
Excuse me? So if you could have a quadratic speed up with quantum computers, do you have a quantum speed up for KSAT?
Yes, for the same reason.
Okay.
Yeah, there's a square root of 2 to the n
Right.
time algorithm for KSAT as well. Yeah. Yep. Yeah, I mean, there's nothing about this reduction that precludes using a quantum computer either. So, yeah.
But it's somehow a different technique. I don't know.
I mean,
Yeah.
but like you can definitely do this, but this is look like to the n over 2 on quantum, but I mean this follows from Grover search. Yeah. So the third problem I want to show you is a graph theoretic one. So this is a K dominating set. So think of K as something like 3. I give you a graph. I want to know if there's a set of size at most Ks, maybe it's 3 nodes, such that set union with its neighborhood is the entire vertex set. Okay. So in other words, I want a small set that has every other vertex in the graph as a neighbor. Okay, so for example, this is a 2 dominating set. And so the naive algorithm actually takes n to the k into the k plus 1. So the exponent's k plus 1 using some tricks you can get about n to the k time for this problem on n node graphs. And I showed that actually, if you could solve this problem even slightly faster than this n to the k time, then you would also have for CNF SAT. Okay. And there are many other theorems like this. There's just like 3 of many others. But I failed to solve any of these problems faster. Okay, but every failure is some opportunity. Okay, so if we just take the contrapositive of the last 3 slides, right? Then we can say that if you believe the strongest switch time hypothesis, which apparently many other people do, then we get optimal, hardness for these polynomial time solvable problems. The orthogonal vectors, partial match, and k-dominating set problems. That you cannot solve them much faster than the algorithms we already know. So, and this is true for a large range of other problems. And so this has led to some theory of hardness within polynomial time, where I have some, again, similar to SETH, like I have some known textbook algorithm for solving a problem that takes, say, n squared time, and I have a bunch of hypotheses and a bunch of reasons to believe that this n squared time algorithm is the best possible, because solving even slightly faster would have a lot of consequences.
Slightly faster, replacing 2 by 2 minus epsilon.
Yeah. So in other words, it's like optimality up to this exponent. Yeah. So yeah, I mean, you could ask for even more kind of fine-grained things, but sometimes like that becomes dependent on your model of computation. So then like it becomes model dependent as to whether you could save a log n factor or not. So like looking at the optimality of the exponent turned out to be like a good thing to look at here. Yeah. Right, so this led to a theory of hardness for problems in P. So if for every delta, we think that CNF SAT requires 2 to the 1 minus delta in time, then we have that orthogonal vectors needs about quadratic time, and then there are many other problems that essentially need quadratic time, all of which are solved in quadratic time. This edit distance one by Bakers and Indyk was quite celebrated. So like computing the edit distance between 2 strings, there's a quadratic time algorithm, and having any reason to believe it could be optimal was cause for celebration. So assuming the strong ETH, or even assuming the difficulty of orthogonal vectors, there's dozens of natural and important problems where the simple quadratic time algorithm just can't be improved. And there's many more developments in fine-grained complexity beyond this, but there's even more to say about SAT. So let me move on to something that really started the last time I was here at IIS as a postdoc in 2008, 2009. So let me tell you about how I accidentally became an expert in circuit complexity. So we were talking about like solving SAT faster, but there's an entire research area on solving various MP problems faster than their naive bound. And there's a lot of beautiful like techniques that people use, and they all like sort of exploit the knowledge of the problem in some interesting way. So at IIS, when I was a postdoc, I was very interested in these kind of questions, like sort of solving KSAT faster, solving, say, Hamiltonian path or maximum independent set faster. But it was very hard to get other people interested in it. And this really made me wonder, and maybe some of you have been wondering, so what? Right? Like, so what? They still take exponential time, right? Like if I improve 2 to the into 1.9 in time, I mean, maybe I improve like the constant, like I improve the length of the things I can solve by some constant factor. But, somehow I had a feeling that this is a fundamental problem, right? The problem of beating exhaustive search, just not trying to get a polynomial time algorithm for an NPR problem, but just beating the obvious algorithm is fundamental, but I don't know why it's fundamental. So then I started reading textbooks and papers and just asking, suppose I could get slightly faster algorithms for every NP problem. Would the rest of theoretical computer science change at all? Could I resolve a problem in a different area that people actually care about? Because they clearly don't care about these things, okay? And it turns out, yes. And there's a very compelling reason to look at algorithms that barely beat exhaustive search, a very compelling complexity theoretic reason for this, okay? So let me describe a particular type of NP problem that's useful for complexity. It's a circuit satisfiability problem. So it's a generalization of SAT in a natural way, but to just say a logical circuit. And the way the logical circuit is wired up doesn't matter so much. I give you some description of a logical circuit with n inputs. I just want to know, is there some assignment to its inputs that make it print 1? Let's just say it's got a single output. Okay.
What is the logical circuit?
Oh, it could be in CNF. It could just simply be like a directed acyclic graph with like ands and ors and knots on it. I'm being sort of deliberately vague. It's computing some Boolean function, and that's all. And it has some inputs and it has a single output. Yeah. But you could think of this just very generically. I restrict the class of logics that I look at in some way, and then I want to know, can I solve this SAT problem faster? And the Cook-Levin Theorem shows us this problem is incomplete already for these like funny CNF things, these ands of ors. And of course, it can be solved by brute force. But the question is, so for what kinds of circuits? What kind of restrictions can I put on logic circuits so that I get a faster algorithm? Right? For K-CNFs and for pre-CNFs, the inputs to this KSAT problem, we know faster algorithms, right? We have very simple ones. But another question is, if you have a class of circuits and you manage to solve SAT faster for them, does this have any implications or consequences about how efficiently those circuits can compute functions? So does it say anything about like the expressivity of those circuits to compute functions themselves. If I can solve the SAT problem for this thing, does that give me a limitation on what this thing can compute? This is the question. It turns out the answer is very much yes. So let me tell you a little bit at a high level about circuit complexity, just because it's if you haven't seen it, it's quite different from like the usual models with Turing machines. So in the algorithm model, we have some Turing machine. It takes in arbitrary long inputs and gives us some answer. So it naturally computes a decision problem that takes bit strings and outputs a bit. In the circuit model, right, the thing that I'm looking at, it's a finite object. It's got takes a finite number of inputs and outputs a single bit. And what a computer decision problem, we just simply define an infinite circuit family. We define a separate circuit for each input length. Okay, so we have some circuit C sub n, which we run on inputs of length n and give us the answer. Okay, and so now we're asking like, okay, what can circuit families do? What decision problems can circuit families compute? Okay, but this sort of question becomes very hard because this is effectively an infinitely long description. On any input of length n, you might only be looking at some finite number of bits of the description, but it's an infinitely long description. And so the usual methods of recursion theory and computability theory go out the window when you sort of have infinite length descriptions. And the big question in circuit complexity is which natural interesting functions require large circuit families where each C sub n must grow, say, exponentially n, or even super polynomial n. Okay, and this is a wide open question by and large. Okay, so I mean, one answer to this question is well, most functions, if you quantify most by like picking random functions, well, they will require large circuits. Right, so a simple counting argument shows that with high probability, if you randomly choose a function, just flip a coin for all the possible inputs, then yeah, you'll need about 2 to the n over n size to compute it. Say if all of the gates have fan in 2, something like that, you have 2 inputs coming in. And so if you just pick a completely random thing, you can't compress it down to a small circuit. It's just a simple counting argument. There's nothing more to that. But random functions are, they're not the kind of functions we want to solve. So the question is like which natural functions, like SAT or something like that, or your favorite NP-complete problem, which do these exhibit exponential circuit complexity or not? And this is a very difficult question, but it's one of the primary questions of circuit complexity. Is trying to understand like which functions computable by Turing machines, by algorithms, need large circuit families. So there are many reasons why one might study circuit lower bounds, but one reason you might not know about is that if you manage to prove like that circuit families need very large sizes, then you can remove randomness from randomized algorithms. So this is a collection of theorems that obvious best known for. If there's a decision problem computable in exponential time that requires one of these circuit families of exponential size, then effectively whatever you can compute in a certain time with randomness, you can compute deterministically. You can remove the randomness. Okay? There are many results in this direction. And the high-level idea is if a function looks random to all circuits, then you can somehow use it to construct a pseudo-random generator where you can just replace the true randomness in efficient computation with the output of this deterministic function. And so this sort of hypothesis is widely believed. And this is yet another motivation to prove circuit lower bounds. There's others, but this is one of the ones that y'all should be aware of, for sure. Okay, so what did I do? So I developed a program where if you could even get slightly faster circuit set algorithms, slightly faster than 2 to the n, then you could use it to prove limitations in circuit size lower bounds on circuits. So the general setup is, suppose I have some, say, Turing machine, and it runs the 2 to the n over some polynomial amount of time. So this is like much weaker than 1.9 to n. It's just like 2 to the n divided by polynomial. Suppose that there exists such an algorithm, and for every circuit that I give it, it can correctly decide the satisfiability problem, yes or no. Okay, given this kind of statement, I can turn this into the following kind of statement. There exists some function derived from Turing machines, it's an algorithmically computable function, whereas for all circuits trying to compute a finite slice of this function, so restricting this function to some input length n, those circuits cannot compute the function. So almost every slice of this function requires large circuit complexity. Okay? So it's a way of taking an algorithmic hypothesis, a way of like taking methods for circuit analysis and turning them directly into circuit limitations. Okay? So, and there are analogous results hold for Boolean formulas and other circuit classes. So like for lots of different classes, if you had like a Boolean formula, like a logical expression, you solve the SAT problem just for that. Then you would, on the other side, you would get lower bounds against formulas instead of circuits. There's an extremely generic collection of results of this kind. So this could also explain why it's difficult to analyze SETH algorithms even when they work, because they are effectively like implying like some limitations on the circuits that they're analyzing. So this led to a failure, but this failure is maybe not so bad. Okay. So I found some cool consequences of improving exhaustive search. I found that, okay, if you could solve these SAT problems slightly faster, you would actually have big implications in circuit complexity, but no one believed that these results could prove the lower bounds. So they're like, wow, if you could improve over exhaustive search, then you could prove circuit complexity lower bounds. Well, great, since we're never going to prove circuit complexity lower bounds, that means you're never going to improve exhaustive search. Nice theorem. Yeah. So then I had to start learning circuit complexity because I'm like, I think that this could go somewhere. So then in 2010, I had yet another approach to trying to solve CNF SAT faster than to the end time. And just the high level idea was I was trying to express the SAT problem as some algebraic problem. So some problem of multivariate polynomials. Then I want to use like fast matrix mold or FFT, things like this to evaluate this polynomial quickly and somehow speed up the search in one way or another. And this failed. And in fact, the CNF SAT algorithms I got, which are even worse than the best ones known. However, this algebraic approach turned out to be very generic, like much more generic than solving CNF. So they work for much more expressive logic than just a CNF. So I showed that SAT for something called ACC circuits. For the purposes of this talk, ACC means annoying circuit class. It's just something that was like people just simply could not analyze for decades. So I got a slightly faster SAT algorithm for that. And then the next day I showed that this implies a circuit lower bound non-deterministic exponential time is not an ACC. It was just a notorious open problem in circuit complexity, and arguably more interesting than SETH being true or false. But yeah, so sometimes even if you fail, you can still get a Gödel prize if you just keep, just to see what happens. Okay. Yeah, so there's an entire literature now of circuit complexity lower bounds which proceed by proving one of these nice arrows of implication and designing an appropriate SAT algorithm. But yeah, maybe I should try to give some heuristic for why this could possibly be true. Like, why should improvement over exhaustive search tell us anything about the impossibility of computing some function? So, see, the idea is that a faster circuit SAT algorithm reveals a weakness in a small circuit. So, in some real sense, a small circuit can't obfuscate the all zeros function as well as a black box can, if you have a SAT algorithm, right? If it's unsatisfiable, then it's just computing the all zeros function. If it's satisfiable, there's some input which makes it print 1. If you can do this faster than just trying all the possibilities, you're somehow doing better than just querying the black box. So to imagine there's two kinds of SAT algorithms. One where I give you the full description of the circuit and you run slightly faster than exhaustive search. Another where you just can insert inputs and see an output. Okay? So it's not hard to show that like, if, I have some algorithm that's just working on black boxes, taking an input and getting an output, I can always cook up some box that requires the algorithm, whatever strategy it has, to query this box to the end time, right? Just cook up some box that, no matter what the algorithm A asks for, just say 0, 0, 0, and then maybe flip a coin at the end, like once you reach the final input you're asking, okay? So in the black box setting, like you need to the end time. So therefore, a faster circuit set algorithm, it demonstrates some concrete difference, right? And like having the description and understanding, like having this sort of white box circuit problem in this black box one. So this is some weakness in circuit. This is some heuristic, but if you, I can definitely tell you more later if you want. So in the remaining time I have, at what point should something?
Have a good 5 moments.
5 minutes. Okay. Yeah, so I'll say a little bit about.
But if you prove P not equal to NP or this.
If I prove P not equal to NP, then I get more time?
Yeah.
Okay. Okay. I can't promise that. Yeah, I mean, I'm sorry, you will not be satisfied with this talk. Okay, but yeah, so yeah, the remaining time, I'm going to talk about some new connection that I found. But in like a 1-slide summary, it's one of these kind of win-win things. So at least one of the following things is true. So either an extremely simple function needs exponential size depth to neural nets. So this is a wide open problem. So depth 2 just means that I have, say, Boolean inputs. I have these kind of linear threshold functions that are computing a linear combination of the inputs and checking whether at least a threshold. These go to some linear combination that's just trying to compute a 0, 1 value. So either an extremely simple function, like it's essentially a CNF, needs exponential size neural nets, so the major open problem, or this very simple function actually has sub-exponential size depth to neural nets, and we can use this to get a deterministic algorithm for CNF SETH running in this much time. Okay, so in fact, this, like having sub-exponential size depth to neural nets for this simple function would in fact solve the orthogonal vectors problem in the linear time, which would give this. So it would be a major refutation of SETH. It's such a strong SETH algorithm that this itself implies circuit complexity lower bounds. So it's like you get a circuit complexity lower bound in either of the disjuncts. Let me see this one. Yeah, so if the so-called disjointness function, which I can define for you if you ask, if it has a depth to neural net family with a sub-exponential number of wires, then this K-SAT problem can be solved in square root of the search space. And so as a corollary, you either get that this simple function needs very large neural nets, or you get new circular bounds from SETH algorithms. And indeed, the proof is that either SETH is true or SETH is false, and then you get circular bounds from falsity. Great. Okay. Let me just jump to the conclusion. So although this SETH thing is unfalsified for now, there's many different directions that and results that I approve, probably more important than refuting it. Of course, I've had many more failures that were simply failures with no apparent opportunities. Complexity is a tough subject, but I guess an open problem for everyone is, yeah, I mean, how do you find opportunity in failures? Like, what are the catalysts for your research? What kind of problems do you have that if when you think about them, you get ideas and you get motivations? Yeah, what are the muses that help you generate ideas? So over the years, I've tried to deliberately look for things that, like, no matter how it turns out, like, I will be able to prove the result no matter what, because it's very difficult to even get intuition sometimes about what should be true or false. So thanks.
Questions?
So if you take the your Boolean corollary and you have two hard functions,
Yeah,
then you kind of combine them,
yeah.
you get a like explicit function that is hard.
So what happens is like in one disjunct, you get some exponential lower bound for like neural nets. In the other disjunct, you get like a superlinear lower bound for another kind of circuit class.
Okay.
So they're like, yeah, they're like, oh, yeah, like I can't, I tried to merge them, yeah, into like one Uber lower bound or something, but yeah. But, yeah, I mean, the point is lower bounds hold no matter what or something. Okay.
More questions? Okay, thank Ryan again.